Hi algebra students. Today we're going to be taking notes on simplifying radicals. So this is going to be page 5 and it's actually going to go over to page 6 in your notebook. We've got a lot to get through today, so at the top you can just write simplifying radicals. So first let's talk about what it means to simplify something. It means to make it look nicer, make it look cleaner. When we simplify fractions, we deal with smaller numbers, and so that's exactly what we're going to do today. We want to be able, when we're calculating something, it's easier to deal with smaller numbers than it is with large numbers. Now, this word radical, we have to define. This is not like radical like cool dude, but this is radical as in this symbol. So normally we call this a square root symbol. However, in general, this symbol, this check mark with a hat, is called a radical, and it has a couple of different parts. Sometimes out in front here, you'll find a number, maybe something like 4. We call this the coefficient. So that's the number that sits on the outside of a radical symbol. There's also right in here, there's an empty space, and we actually call that the index. And we'll talk a little bit more about that in just a second, but just so you know, you can actually stick a small number in there, maybe like a 3 or even a 4, inside that little check mark. Now, most of the time, when we're dealing with square roots, think about squaring means an exponent of 2. When we're dealing with just a plain old radical symbol, something that looks like this, we're dealing with a 2 in there. And so because square roots happen so often, we don't usually see that. But just so you know, in that empty space right there, what we would call the index of a square root, there's actually an invisible 2 there. And again, we'll talk about that more in a minute. Also, normally we have a number under the square root, right? Square root of 16, square root of 100. We call that number on the inside here the radicand. Now, so those are just a few vocabulary words for you to keep in mind as we go throughout this. Again, the radical symbol is the check mark with the hat on it. We call that a radical. Coefficient is the number on the outside. Index is the number that sits in between the check mark, a very small number there, and then the radicand is going to be inside. And remember, when the index is not written, it's actually an invisible little 2. So what we're going to be doing today is simplifying radicals, meaning we're going to be simplifying things like the square root of 80. Now you might be thinking to yourself, well, the number 80 is not all that large, but when we start to do calculations with the square root of 80, notice that 80, number one, is not a perfect square number, right? We cannot take the square root of the number 80 without a calculator. We don't know a number times itself that would equal 80. So because 80 is decently large, we want to be able to do what's called simplifying it. We're also going to deal with larger numbers, something like maybe the square root of 750, or even we could stick a number in here, something like the cube root, right, of 750. So we're going to be simplifying large numbers, large radicands underneath the square root symbols like this. Now, before we get into this, we have to do a little bit of review of something that you probably did in elementary school. And so before we get back to simplifying this stuff, we have to know something about the skill of prime factorization. Now, you may not have called it that in elementary school because that's a pretty big word, but you've seen this before. Maybe you called it a factor tree. Let's do an example real quick. So something like, let's talk about the number 120. Now 120 is a pretty decently large number, but what we can do is we can break 120 down into what's called its prime factorization. Now, the word factor means two things that multiply together to get 120, right? A factor means we can multiply something to get this number. So what we do, and again, you may have called it a factor tree, is we're going to break down the number 120. Well, think through your brain. What are two numbers that will multiply together to get 120? Now, there's lots of different answers, and it really doesn't matter which two you pick. You might choose 12 and 10, for example. I'm going to actually choose 24 and 5, and again, you can use a calculator for this, so you can just start dividing 120 by numbers. But if you type it in your calculator, 24 times 5 is 120. Now, the word prime here is key because when I get a prime number in my factor tree, I'm going to circle it. Because think about the number 5, for example. 5 is prime because the only way we would be able to break a 5 down into its factors would be 5 and 1. Now, if I kept writing 5 and 1 and 5 and 1 and 5 and 1, that makes my tree redundant. And so when you get to a prime number, it's almost like coming to the end of a root of the tree. You can stop right there. If it's prime, you stop. So 5 would only break down into 5 times 1, so we can stop here. However, 24 has some factors that we can break it down into. So if we think about 24, the factors, again, there's several here you could choose from, 12 and 2, 6 and 4. I'm actually going to choose 8 and 3. And so we ask ourselves again, as we go through this process, is 8 a prime number? Well, no. 8 has numbers it can be broken down into, but 3 is, because the only thing I could write from that would be 3 and 1 again. That means it's prime. We can still be breaking down the number 8, though, and so I'm going to draw, again, another part of my tree. 8 can be broken down into 2 and 4. We notice that 2 is a prime number because 2 and times 1 is the only way to get 2. However, 4 can be broken down one more time. And so 4, we can break that down into 2 and 2. And finally, we can't break these numbers down anymore. And so we have arrived at, again, what is called the prime factorization of 120. And here's what this means. This means, and you can check this in your calculator if you don't believe me, all of these prime numbers that you have circled, and that's why it's important to circle them. Don't get lazy on me. Make sure you're circling them. When you find a prime number and you circle it, and then you look at the end of your factor tree, all these prime numbers that you've gotten, if you were to do 2 times 2 times 2 times 3 times 5, guess what you would get? 120. And so this multiplication, the sort of string of a bunch of multiplication actually equals the original number that we started with. Now, again, remember, our whole goal here is to simplify. So the reason we need this skill is that 120 is a decently large number, but 2, 2, 2, 3, and 5, those are all decently small numbers. And that's going to be important as we simplify a radical. So just real quick, before we move on to actually simplifying radicals, I just want you to practice a prime factorization with me. So maybe you want to pause the video. Let's use the number 72. See if you can do the prime factorization tree on your own, and then you can pause the video and then restart the video and check yourself. So I hope you took time to pause the video. And again, your answer may look a little different from mine as far as the factors you chose, but our final answer should be the same. So for 72, lots of things that will multiply together to get 72. I'm actually going to choose 36 and 2. You might have chosen other numbers here. I'm going to circle 2 because 2 is prime. 36 will break down into 6 and 6, neither of which are prime. They can be broken down again into 2 times 3, which are both prime, and also, well, 2 times 3 again, which are also prime. And so notice I have no other numbers left to break down into prime numbers, and so this is as far as I can go. And you can always check yourself in the end that 72 is equal to all of these circled numbers multiplied together. Now, I am in a habit, and it would be good if you would get into the habit as well, of writing these prime numbers in order from least to greatest. So notice up here how I wrote 2 times 2 times 2 times 3 times 5. Down here, even though I've got like a 2 and a 3 and a 2 and a 3, instead of writing 2 times 3 times 2 times 3 times 2, I'm going to put all my 2's together and all my 3's together. That will make more sense in just a second when we start simplifying radicals. But it will be nice if you have those numbers in order from least to greatest, also all kind of grouped together. So notice we have 3 2's and 2 3's, and if you multiply that together, you do get 72. And so that is called the prime factorization. And prime factorization is the skill that we are going to need to know in order to fully simplify radicals. So I told you that our notes were going to go on to the next page, and so if you will flip over to what we are going to call page 6, which will be the back of what we just did. You can sort of see my notes through there. So number 6, page 6, continue simplifying radicals. So I'm going to give you 3 steps that you're going to follow every single time that you are simplifying a radical. So we're going to say step 1, step 2, and step 3. All right, so the first thing you are always going to do when simplifying a radical, and remember again, we're dealing with symbols that look like this. So simplifying a radical, the first thing you're going to do is find the prime factorization of the radicand. Ignore that. Find the prime factorization of the radicand. Remember, the radicand is whatever is in here, right? It's the inside number underneath the radical symbol. All right, that's step 1. Step 2 is to pay attention to the index. And in parentheses, I'm just going to put groups. And I'll tell you what I mean by groups here in just a second. But remember, the index, if the radicand is the question mark here, then the index is going to be this little tiny number here. Now, if we do not see a number, do you remember what it is? Right. If you don't see a number there in that spot, that actually means it's a 2. But you could have a 3 or a 4, etc. All right. And then step 3 is you're going to circle your groups and bring outside radical. Now, again, that step is going to make a whole lot more sense when we actually do an example. So, keeping those 3 steps in mind, let's look at example number 1 of what does it mean to actually simplify a radical. All right, so we're going to go back to the radical that I talked about at the very beginning of these notes, which was the square root of 80. Remember, we wrote that on the other side of the page here. So simplify the square root of 80. So actually your instructions would probably say to simplify. I'll squeeze that in here. So that is our goal, is to simplify this. Again, 80 is not a very large number, but also if I'm going to be doing math with this, I would much rather deal with a smaller number than 80. And so we are going to first follow step 1, find the prime factorization of the radicand. So even without rewriting 80, and you could go off to the side if you wanted to, but you could actually do it from here. So 80, I'm just going to start breaking that radicand down. 80, you could think of a lot of different things that could go into 80, maybe 8 and 10. I'm actually going to choose 2 and 40. And so remember, our goal is to break these numbers down, circling the prime numbers as we go. So 40 would be 2 and 20. Again, you can use a calculator for this if you'd like. 20 will break down into 2 and 10. And 10 will break down into 2 and 5. Didn't circle my 2's. All right, and so we have arrived at the end of our prime factorization. Now what we're going to do is we're going to actually rewrite this square root. So the square root of 80, and I'm going to write it over here off to the side, the square root of 180 actually equals, I'm going to jump over my instructions here, the square root of, now keep in mind that 80, this is telling us that 80 is actually 2 times 2 times 2 times 2 times 5. So what I'm going to do is I'm going to replace the number 80 with that string of multiplication now beneath this radical symbol. So 2 times 2 times 2 times 2 times 5. Keeping in mind, try to keep your numbers together. Try to keep it from least to greatest. All right, so that is the first step. Find the prime factorization of the radicand, and so we're just going to replace 80 with these numbers that we found after we found the prime factorization. Now, step 2, pay attention to the index, and this is going to tell us about groups. So if we look at our radical symbol, what is the index here? It's invisible, right? I don't see a number there, and so if I do not see a number there, that means I'm dealing with a square root. Square roots are so common that actually there is an invisible 2 there, because squaring something means 2 to the second power. So I'm going to write in my little 2. You don't have to. You can just remember that if you don't see anything, it's a 2. And that's going to tell me about groups. Now, here's what this means. This means that everything underneath this radical symbol needs to be put into groups of 2. Because think about what it means to square something, right? If you do 1 squared, that's 1 times 1. If you do 2 squared, that's 2 times 2. If you do 3 squared, that's 3 times 3. And so what this is telling me is how many numbers multiplied together are in one group. Well, notice what I've got here once I've done my prime factorization. Do I have groups of 2 numbers each? Do I actually have numbers being squared? Well, yeah, there's a 2 times 2 right here, right? That's 2 squared. It's a number times itself. Do I have another group of 2 numbers together? Well, absolutely. There's another 2 times 2 right here. So I'm going to circle them in the groups. As long as it's a number by itself, I'm going to circle that, because what that means is that this number is being squared. 2 squared, 2 squared. Now, can I circle 5? Well, no. 5 is on his own. If I had a 5 times 5 here, absolutely, because I'm circling groups of 2. But in my prime factorization, I only had 1 5, so I cannot circle him. He has to stay. Now, that's step 2, so pay attention to the index and the groups. If this is a 2, you're going to circle groups of 2. We're going to do a 3 here in a minute, and we'll talk about what that means. So it says circle the groups and bring outside the radical. So step 3, we have circled our groups, and what I'm going to do is I'm actually going to move these groups outside of the square root. Now remembering, a square root and a perfect square are opposites, right? We've already talked about that in a previous video. And so think about what 2 times 2 is. 2 times 2 is really 4, right? What is the square root of 4? Well, the square root of 4 is 2, right? So when I take this group outside, that's what this is saying, bring outside the radical. What I'm actually doing is I'm taking the square root of 4. Well, the square root of 4 is just 2. So I'm going to write it outside as the coefficient, right? Remember, the coefficient lives out here in front. So square root of 4 is 2. Square root of another 4 is another 2. So I'm going to take this out again. The square root of 4 just becomes a 2. Now I'm going to put a multiplication symbol, and I'm going to write this out, and then we'll talk about where all these numbers came from. Now, can I move the 5 outside? Well, no, this is the square root of a 5. It's not the square root of 5 times 5 or 25. So I'm going to rewrite my radical symbol, and the 5 has to stay inside his little house here, right? Inside the radical. So again, think about what we've just done. 2 times 2 is 4. The square root of 4 is 2. This was a group of 2's, so I moved a 2 outside. Another group of 2, which would have been 4, square root of 4 is another 2, now on the outside. We've actually taken the square root of these numbers. Now, on the outside, in the coefficient spot, I actually have 2 times 2, which is just 4. And so I have 4 times the square root of 5. And guess what 4 times the square root of 5 is equal to? That's exactly the same thing as the square root of 80. Now, if you're curious to check yourself, which I always encourage, if we open up Desmos, either on your phone or on your calculator, and if I were to type in the square root of 80, I actually get this really long decimal number. And we're not so much interested in the decimal number as we are, remember, about simplifying it. Because dealing with a square root of 80 when I'm doing math is actually probably easier than even dealing with 8.9427191, right? But I can check myself to know that these two things are actually equal. If I start with what I had and type it in the calculator, get the decimal, and then I type in my final answer, so 4 times, and you can hit the time symbol if you want to, or remember when a number is right next to something, it means multiplication. Square root again, and then I type in a 5. Those decimals match. And so it is true that 4 square roots of 5, 4 times the square root of 5, is the exact same number as the square root of 80. And we're going to find out as we move along. You might be asking yourself right now, like, well, what did that do? That looks just as bad as that. As we move further into algebra, it's going to be a whole lot easier to deal with 4 times the square root of 5 because the numbers are small than it will be the square root of 80. Similar to, if you think about, I would much rather deal with 1/2 than 25 over 50, right? It's just nicer numbers. So even though those are the same thing, I'd rather deal with a 1 and a 2 than a 25 over 50, which is why you reduce fractions in, 4th and 5th grade. All right, let's do another example. So that's the first example. Let's do example number 2. So example number 2, we're going to change the index. So let's look at a cube root. So let's do the cube root of 750, which was, again, the number I showed you on the other side. So remember, step 1, find the prime factorization. Prime factorization is going to be two numbers that will multiply together to get 750. I'm going to pick the most obvious ones, 75 and 10. And again, you can use your calculator to check some things or maybe divide 750 by something to see if you can find two numbers that will multiply together to get it. Then I'm going to break down, neither of those are prime, right? We can break down 75 into 25 times 3. It's like 3/4. And then 10, we're going to break that down into 2 and 5. Now, I notice on this line that I've got some prime numbers. So 5 is prime, 2 is prime, 3 is prime. 25 can be broken down again into 5 times 5. And so I've arrived at my prime factorization. So I'm going to go back up here at the top. I'm going to rewrite. Now remember, this is a cube root, right? My index is 3, and the index is going to be important. So the cube root of 750. Why did I write that? I need to wipe that out. So that's going to be the cube root of, and again I'm going to put them in order, so 2 times 3 times 5 times 5 times 5. And so that is my prime factorization written out inside the cube root. My step 2 is to pay attention to the index. Now notice this is a 3. So here, if it was a square root and we took out groups of 2, what do you think we're going to do when the number is a 3? Well, we're going to take out groups of 3 because cube roots, remember, are a number times a number times a number. And so we're going to circle the groups and then we're going to bring them outside the radical. Well, if we look at our numbers here, 2 and 3 are kind of on their own. They're not with a group. But do we have a group of 3 numbers together? Well, yes, 5 times 5 times 5. 5 times 5 times 5 would be a perfect cube, which means we can take the cube root of it. So think about 5 times 5 times 5, what that actually is. Remember, that's a 125. And I can actually take the cube root of it. So again, really all you need to know is, hey, there's 3 5s here. I'm going to be able to move that outside as a 5. So on the next line, that group of 5 comes outside the cube root as a 5, but we're left on the inside, and I make sure that I write a 3 for my cube root. I'm left on the inside with 2 times 3 because they could not come out because I did not have a group of 3. So 2 times 3 is 6. And again, to check yourself, open up Desmos. Now we're dealing with cube roots here, so we've already had some practice with this. You go to the functions menu, miscellaneous, type in my root here. I'm going to put a 3, and then the first one was 750, right? So 750, that's going to give me the decimal, 9 point, all of those things. And then down here, I'm going to type 5. I'm going to go back in and get that cube root, type in a 3 as my index. The cube root of what we got was 6. And compare those decimals and make sure they are the same. Let's do one more example. So just in review, we have simplified radicals first with an index of 2, meaning that once we did the prime factorization, we grouped things into groups of 2 and moved them outside one at a time to the coefficient. And then when we deal with cube roots, we group numbers of 3 and move them to the outside and take the cube root. And the last thing we're going to deal with, so example number 3, is going to be when variables are involved. So for example number 3, we're going to deal with an example that looks like this. The square root of 90 x cubed y to the 4th z squared, or z to the 2nd power. And so when we're dealing with variables, you might first look at that and say, oh goodness, like all of those letters, but it actually does not become any more complicated. We already know how to deal with the number, right? We're going to do with this 90 exactly what we have been doing with numbers. We are going to figure out what is the prime factorization of 90. So let's go ahead and do that. I'm going to ignore the letters for just a second. So 90, we can break that down. Probably the first thing you think of is 9 and 10. 9 breaks down into 3 and 3. 10 breaks down into 2 and 5. the more you do of these, the faster you will get at this prime factorization method. 3 is prime, 3 is prime, 2 is prime, 5 is prime. And so I'm going to go and I'm going to rewrite again my square root. Instead of writing 90, I'm going to write my prime factorization in order. So 2 times 3 times 3 times 5. 2 times 3 times 3 times 5. And now I'm going to deal with the letters. Well, think about what x cubed means. X cubed just means take x and multiply it by itself 3 times. So that would be x times x times x. And think about what y to the 4th power means. That's y times y times y times y. And z squared would be z times z, right? The exponent just tells us how many times to multiply this number. And so because they're not actual numbers, there's no real multiplication to do. It's actually just repeatedly writing that number. So x cubed is going to be x times x times x, and I'm not even going to put a dot between them. If I write letters next to each other, that means multiplication. So x times x times x, and then my y is going to be y times y times y times y. There's going to be 4 of them, and then z is going to be 2 of them. All right, so it's almost just like we're writing out a bunch of letters in the alphabet, but you have to pay attention to the exponent to know how many times. All right, so that was step 1, is to find the prime factorization. We have now, this is called expanding our variables. So we've now expanded them. And so the next step is to pay attention to the index. What is my index here? The index is 2. We can't see it. It's a square root, which means we're going to go through here and circle groups of 2. So 2 is by itself, no group of 2s. There is a group of 3s to move out. And I didn't explain this earlier, but I like drawing this little line. You could even put a little arrow on the end of it, because what I'm doing is I'm moving it outside. That just reminds me that, hey, this needs to go out. 5 is by itself, so we can't circle it. There is, however, a group of x's. So now we have these letters that we have to deal with. So the x's are going to go out. Notice this x does not have a pair, so he's going to stay in. The y's, however, there's a group of 2 y's. That's going to go out. There's another group of 2 y's. Remember, we're moving out groups of 2 because our index is 2. And then there's also a pair of z's. And so the z's are going to go out. And so I'm going to write all of my coefficients first. So on the outside, notice we have moved out a group of 3's. That's 3 times 3 is 9. Square root is just going to be 3. So again, when you move out a group, it just becomes one number on the outside. So 3 is on the outside. There's going to be an x. There's going to be 2 y's, because we moved out that group of y's, which becomes a y, that group of y's, which becomes a y, and we move out a group of z's. So that's left on the outside. Now we're going to check and see what's on the inside. Well, there's still a 2 times 5. 2 times 5 is 10, so I'm going to make that a 10. Again, that came from 2 times 5 is 10. Those are my numbers that are left. And then check out the letters that's left. The only letter that's going to be left is this x, who did not have a friend, did not have a partner, and could not move outside. So he's left on the inside. So on the inside, we've got 10x under a radical symbol. And the only thing left to clean up is, what is y times y? Well, think about how we wrote y to the 4th as y times y times y times y in the beginning. We can actually clean this up a little bit, and this is going to be 3 times x y squared, because exponents are just a quick way of writing repeated multiplication, z, and then square root of 10x. Now, of course, in Desmos, there's no way to check when you're dealing with a bunch of variables, because we don't know what the values of those numbers are. So when you're dealing with variables, you're just going to have to be very careful to make sure that you've got the right amount of variables written. And that is your notes for simplifying radicals. Maybe you need to rewatch that. That's a lot of notes in one video. There's some practice for you to do, and so always rewatch the video if you need to, and go ahead and start practicing.